We had temperature scales. This was the Kelvin scale, not Celsius or Fahrenheit. And it has an absolute zero as a reference, where something has no temperature. It's zero. We discussed it, and so does your book. So I wanted to see what you remember. Oh, I'm in a generous mood. If it has no volume, does it take up any space? And then where'd it go? It would have poofed, right? So yeah, it probably has volume there. There, roll that one out. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right, most of you think it's B. Some still think it's A. B is correct. It has no more energy to give up. So it can still have a little bit of internal energy. Remember, that's different than temperature. That was my main purpose for this. Temperature is a measure of average translational kinetic energy. So the energy must be somewhere else. It has no more of average translational kinetic energy to give up. And so its temperature is zero. That's absolute. That is what absolute zero means. Some people will tell you it has absolutely no molecular motion. Well, they're misinformed. Is that nicer to say than they're wrong? Because actually, a lot of people think that, including scientists that don't have to deal with it, but they learned about absolute zero. It doesn't mean that it can't be moving at all, have some motion. It just has no average translational kinetic energy motion. It's not being translated. It might still be wiggling a little bit. Helium's a good example. Helium doesn't freeze. Theoretically, it can go all the way to absolute zero and not freeze. So there's still motion there. But it has no temperature. I don't know. I know. And nobody's ever approached absolute, or gotten to absolute zero either. Gotten like a billionth of a degree above it, but okay, pretty dang close in my book. But technically, nobody's ever gotten there. It's kind of like an asymptote. Okay. What's another word for heat? If you got this heat down. Like I said before, I hope you get more out of this, which I'm sure you will, but if nothing else, you'll know that heat and temperature aren't the same thing, right? Good. So it's not A. So if you were thinking that, change your answer right now. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Meh. All right, 83% think it's C. Very good. It's that internal energy, which is the total energy. And, yeah, it flows from hot to cold naturally. It doesn't go the other way by itself. Any questions on that? What's internal energy normally measured in? And for that matter, heat. Because we just asked that question. They're both measured in which units? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right, those of you that are answering B for joules, you're correct, but calories is another unit for it. We discussed that, your book discusses that. Food usually lists it, and at least in the United States, it's way more prevalent than joules. So they're both units of energy. 1 calorie is 4.9 184 joules. So 1 calorie is roughly 4 joules. All right, we introduced specific heat capacity. Your clue here, my term for that is thermal inertia. And water has a very high specific heat capacity. What does that mean? Eight, 7, 6, 5, 4, 3, 2, 1, 0. Hey, I'm feeling good about that. The sad part is that roughly half or a third of you don't see all of them yet. It is all of those. So let's discuss them. It requires a lot of energy in order to increase the temperature. Well, thermal inertia, resistance to wanting to change. Change what? It's temperature. And so you're going to need a lot more energy to have a bigger change in temperature. It's compared to something like sand that has a small specific heat capacity. That's going to heat up faster. Think of it that way. When the sun's bearing down on the beach, sand's hot, right? Because it has less thermal inertia. So for that same energy input, solar radiation, the sand will heat up faster than the water. So B, the reverse is true then too. If something has a lot of internal energy, the water has to give a lot more of it up before you see it drop its temperature, where the sand will cool off relatively quickly. Or think of metal. You set some really hot water in your pan, right? Your pot of boiling water. The water takes a long time to cool off, where the pan can cool off a lot quicker, especially if you separate the two so they're not sharing their heat. Does that make sense? And then C absorbs a lot of energy for a small. That's essentially the same thing with A. It's going to require a lot of energy to increase the temperature, and even if it absorbs a lot, there might not be that big a change because it's resisting changing. It has a high specific heat capacity. Is this helping with that term? Okay. One more. Good. Given that, we'll see if we can get this one right. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Woohoo! Copper. It has the smaller specific heat capacity, thus less thermal inertia. So it can't resist the change as much. So it'll change faster. So it says, aluminum's more than twice that of copper. So copper's going to heat up quicker. It'll also cool down more quickly. All right, you can put your clickers away. Okay, at the end we talked about water. How most every object we deal with, when you put internal energy into it, it heats up. You're transferring the heat. the temperature goes up. And physically, it expands. Do you understand why something would typically expand? Yeah, when it's gaining internal energy and getting hotter and hotter. Why would it want to expand most things? You're right. What? Good, you're both saying the same. The particles start, the average translational kinetic energy is increased, which means they're going faster, right? And do you remember the relationship between kinetic energy and velocity? How are they related? What's the directly, linearly, proportion. You remember the formula for kinetic energy? 1/2 mv squared. A side note, big particles versus small particles. If they have the same exact temperature, who's moving faster? The air in the room, for example, we have oxygen and nitrogen are the biggest two. Which one's bigger, oxygen or nitrogen? What do you think? Okay, we'll make it easier. Water. They're connected. I just forgot two. I want to say oxygen is. Oxygen is... Oh, brain fart. Just forgot. Anyway, big particle, small particle. Same temperature. Who's moving faster? Do they have the same temperature? What's the temperature mean? They have the same temperature. What's the same about them? Not specific heat. Average translational kinetic energy. So they have the same kinetic energy. Okay. But what's that tell you about the speed? Very good. What's this idea? Lights on to seal for a moment. And it's right in the shadow. But anyway, they have the same kinetic energy. The one that's bigger will be moving smaller, less, slower. And the smaller one will be moving faster to have the same kinetic energy. Does that make sense? I think that's kind of fun, just because you can just measure something and based on its temperature. If they're the same temperature, then their size tells you who's moving faster and who's moving slower. See how this all relates, builds on top of each other? So that's why they speed up. Temperature goes up, they speed up, they're moving around more and they're pushing, and so they expand. And vice versa when they cool off. Some of that internal energy is transferred out as heat. They have less internal energy. They're wiggling less. The temperature goes down, they're moving less, and they contract. Except for water. Water's a little weird when it's turned into ice. So now back to this picture. Liquid water on the left is more dense because the molecules can get closer to each other. They're free to move around. But when it freezes, it forms a crystal structure with open hexagonal spaces. And so physically, it takes up a bigger volume. But there's still the same amount of matter, right? So what happened to the density? Yeah, the screen tells you. It's less dense. So same matter in a bigger space. And that's why ice floats. And fish are really happy about that. Because if ice sunk, you'd freeze the top of your lake, right? And if it was more dense, it would sink to the bottom. And then the cold air temperatures freeze the next layer, and it sinks. Next layer sinks. And slowly the whole lake would build up and be a solid thing of ice, and what are the fish supposed to do? Die. But now think of it this way. Ice is less dense. This is good. All right. So the water gets cooled. What happens to water when it cools? Not freezes, but cools. It gets more dense. And so where does it go in the lake? Yeah, it sinks. So the cold water goes to the bottom, but it's still water. Then the top gets cold, and it sinks, cold. And now all of it gets cold. And that magic temperature is 4 degrees Celsius. That's where water is the most dense. So the whole lake will be 4 degrees Celsius before the top will start freezing. Because think of it, it's all 4 degrees now, right? Okay, now the top gets even colder. And it goes to 0 degrees, and it's turned into ice. Well, that's less dense. It stays there on the top and floats. And so you only get ice on the top layer. And you know right away now, if you see a lake or a pond that's frozen, you automatically know the temperature of everything below it. It's 4 degrees. It's still water. Fish can still survive. They are getting colder. It is 4 degrees, but they can live with that. It can completely freeze. You've seen the whole thing. I mean, the ice can get thicker and thicker, but from the top down. It won't freeze the ice down below and then rise up. But if you have a shallow pond and it's really cold, the whole thing can freeze, and then the fish are toast. Right. Why would they never freeze? If they're so deep. It's a reason. But well, you know, in terms of physics now too, and the book. Well, yeah, the specific heat of water resists the change a lot. So it takes a whole lot of pulling of energy out before the temperature drops. But it could be really cold for a long time, like in Antarctica or something. And so it can happen. But you have a whole lot of water, don't you? Remember this guide to our thinking? So this of water means you're going to need a whole lot of this to have much of a change here. However, if you have a whole lot of water, this gets spread out amongst all of them. And so it has less effect per molecule. So that's why if the lake is big enough or deep enough, it takes a really long time to add enough energy or to pull energy out to drop the temperature enough to freeze it. But a small, shallow pond, I've seen completely frozen. Good. That's why it takes longer to heat up a big pot of water than a small pot of water. It's still water. It boils at the exact same temperature, but you got more of it. So it's going to take more heat. Yeah, Tom? Yeah, if water is moving, that's going to affect it. Absolutely. So another picture up here. In between 0 and 4 degrees Celsius, or from 4. At 4, water is the most dense. It starts, it's still in that state on the left there. It's as cold as it can get, so it stops wiggling around and it contracts, but it's still water. And then it's as tight as it's going to get. But as soon as it starts freezing and making ice crystals, which can start about 4 degrees Celsius, then you start getting a mix like this. And you still have the water around, and like there's 2 ice crystals. And they take up more space. So the volume expands slightly. It becomes a little less dense until, of course, it'll all be ice. Or it's even all crystals, takes up even more space. So anywhere from 4 is at the bottom. So think about it. You're down here. What if you take 4 degrees Celsius water and heat it up? What happens to the density of it? We're going to start from 4 and heat it up. It's still water at 4. Okay, I heard it less dense in 2 places. And I forgot what you said. First contract and then expand? From 4, right there on the left, they'll just start expanding. So it'll decrease its density because the volume's getting bigger as you heat it up. Let's go the other way. If you freeze it from 4, what starts happening? Now it looks like this. You've increased the volume again, but because of ice crystals this time. So 4 is at the bottom. It's the most dense at 4. So if you heat it up from 4, it starts expanding. And if you freeze it from 4, it expands too until it's all ice at 0 degrees. Then what happens at 0 if you keep cooling it off? It's all like this on the right. Whoop. Like that on the right. What happens now if you keep pulling energy out of that? Yeah, it'll get more dense. Pull those ice crystals closer and closer together. It'll contract like everything else we're used to. But water between 0 and 4 is just a little, it's different than everything else. And we're grateful it is. Picture from your book. And number 2 there, the bottom where he's at 4 degrees. This is volume versus temperature. So you actually expand either way from up to 4, at least to 0 till it's ice, or on up as water. Going this way, but actually this way. Does that make sense? Any confusions? Let me repeat anything? Since water is so ubiquitous, my friend, I think it's cool to understand this. All right. So, what do I want to do next? I had that much in my head. Okay, so the rest of, nope, that's right, this one. It wasn't cooled off in time, Ron, so I thought, let's do it again, shall we? They're both at room temperature now, the ball and the ring. So let's heat up just the ball this time. It's metal, so it has a low specific heat. So as I add heat to it, energy, it doesn't take much to increase its temperature. All right, that should be hot enough. Theory, it expanded, right? Yeah. Now it can't go through, as we saw the other day. And what I always threaten other instructors is after you do this demo, don't leave it like this. Why? Break the ring? Well, what's going to happen to the sphere once it cools off? It'll shrink, but it stays stuck in the ring, darn it. It actually won't clear it. It's such tight tolerances. It's really annoying. But now the ring is expanded enough it won't fit through. When it cools back down to room temperature, it just barely fits through. But that's one way that he makes some joints. You can like heat something up or cool something off, put them together, and then let it happen. And they're on their own expansion can make it than you could ever force it to be. Think of telephone lines as a good example. I think your author used this one too. Do you want to hang telephone lines between 2 poles on a really hot summer day or a really cold winter day? Cold winter day? How come?
Because then when they contract, they'll be
so it's winter day, it's cold, so they've contracted, right?
They'll be as contracted as possible and contract.
Yeah, they're contracted as possible. They're hanging wires. So that means if you well, that depends on how you hang it. I didn't put a caveat in there. Reasoning off in my mind. If you make it tight on a winter day, would that be good or bad? Yeah, if it doesn't get any colder, you're okay, right? Because it won't contract anymore. Because when it heats up, it's going to expand and sag. But let's say on the hot summer day, you made them nice and tight. Well then, as it gets colder in winter, what's it going to do? It's going to try to contract. But it's already as tight as it can be. It's going to pull the poles over. So you have to think of things like that. You've probably seen the spacing between roadways, especially on bridges. Sometimes there seems to be huge gaps. There were in railroad ties, not anymore, but they used the railing. And that's for expansion and contraction with the weather. They know it's going to shift and move. And if they're not allowed to, they're stuck together, Remember our bimetallic strip? If one expands at a different rate than the other, it'll cause stress and break. Right. So now we have three methods to transfer heat. I think you guys understand it, how it can move and whatnot, but there's three main methods for causing this internal energy to flow. There's conduction, convection, and radiation. Or as my daughter was taught, density, I just love density. Conduction, convection, radiation. There you go, L'Oreal. So conduction is, I'm pointing to the camera in case you watch. When they're in physical contact. Particles are up next to each other. I'm touching the table, so heat can flow. Remember, there's particles in here, there's particles in here, and as they interface, they're hitting each other, right? The faster moving ones are transferring their energy to the slower moving ones and making them speed up, increasing their temperature, and vice versa for the other. That's all there is to conduction. There, we're done. Most people understand, huh? Here's a couple examples. I wrapped tightly a piece of paper around this. This side's wood, and this side's metal. So let's split the difference here. What will happen if I heat it up? Let's just start easy. What if I heat here at the metal? Can I stay holding on to this? Sure. Metal conducts heat really well. Here, you brought up conductivity. And that's how well it transfers the heat through it. And metal does that really well. And so it all gets hot. I don't want to touch it anywhere now. But wood's a good insulator. It does not conduct heat very well, like styrofoam. Air is a very poor conductor of heat. It's an excellent insulator. So heat is not transferred very readily through air. But now, I'm taking a guess at least, I'm going to spread the flame over the wood and the metal. Where'd the paper get burned? On the wood. Why? You should have enough knowledge now. Think about it. Go ahead, Josh.
Because the metal absorbs the heat faster.
Very good.
So it doesn't burn the paper.
Very good. The metal absorbs the heat faster. Which one has the lower specific heat capacity? The metal. That means it has less thermal inertia, less resistance to change. So it heats up faster. That means it absorbs the energy. And so the paper doesn't. The heat is transferred to the metal more quickly than the paper. But the wood's the opposite. It resists changing. And so where does the energy go? Into the paper. You can see it singe, can't you? Another fun way, another camp out. I've boiled water in a paper cup. Has anybody done that or tried it? You can actually boil water in a paper cup. So brand new candle here. Let's light her up. We're going to take a balloon that I blew up. I bet you know what's going to happen. There's a water balloon. I don't have my mop ready. Bet you can guess what's going to happen. And so as long as you're not like, right in a rip-roaring fire, think of water in a paper cup could do the same thing. And it would take, you have to do it a little more slowly, but eventually the water could start boiling. Let's see, do you see any singe marks here? A few singe marks. But that's because the heat's going into the water. The water has a high thermal inertia. And so it's taking in all the heat. It's happy. And it keeps the balloon from popping. So, there we go. A little transfer of energy. Review specific heat. Here's my favorite though. I'm sad the space shuttles are no longer in existence. But we'll move on, progress. And this is an actual tile from the Columbia space shuttle. This one never made it into space, but they had backup material ready because they had to replace tiles every time. So this was going to be on the space shuttle, and since they didn't have any need for it anymore, they cut them up into small pieces for educational purposes. So this is, put at the front of the shuttle, so when they're re-entering, they don't burn up. Because they want this to absorb the energy instead of the astronauts inside. This is an excellent insulator. It's 99.9% air. Air is one of the best insulators we know. It's mostly, the rest is made up of silicone fibers that are just trapping the air. Let's heat it up. I'll hold this corner. It's at room temperature. It feels fine. And then I'll heat up this corner. It's glowing. It's several hundred degrees Celsius, that corner. But I don't feel a thing. It does not conduct through the tile to my finger. Still, if we measure this, let me see. See where we're at. 400 degrees on that corner. Where the corner I'm at? 80. Now that's in Fahrenheit. It's good Celsius. So yeah, I'm just above room temperature, like 25 degrees Celsius at the corner I'm holding. And the other side is, well, now it's 100. Let's see what it got up to. Degrees Celsius. But I don't feel a thing. Now, that's impressive. Let's hear it for NASA. And it's because it's still hot, I'm putting it on this fire brick so I don't hurt them. So that's conduction. Convection is where instead of energy being transferred from particle to particle or within the material, that's conduction. Convection is the energy is transferred by movement of the heating substance itself. That means if you heat up some air down here, what's that do to the air, the particles in the air? Heats them up, their temperature increases, they physically start to move faster. And if they're moving faster, they're not constrained to a volume. They expand. What happens to the air's density? It decreases. What happens to this parcel of warm air then? If it's less dense than the surrounding air, it's buoyed up and starts to float. It rises. That's why you've all heard that, right? Hot air rises. That's why. So there's hot air moving up the chimney. Cold air comes in and takes its place. It's placed with fresh oxygen. And that's convection. You got the air moving around. It warms up this air, and it moves, and transfers that heat to the air up top. And then the cold air comes in. And to help visualize that, I have some paper bits. So let's just throw them in the bottom and see what happens. They ride the air currents up the top because the hot air is moving up. That's all there is to convection. You heat up a substance, and usually it's fluids, gases or liquids, and they move with that heat. And then eventually you heat up the whole room. Close the doors. Now what happens to the hot air when it gets up top? It cools. And if it cools, what happens to its volume? Because they're not moving as much, right? So it contracts. It becomes more dense, sinks back down. That's how you can get this to continually go. It's a convection cycle. How many of you have a fireplace in your house? What do you always have to do before you light it? Laugh was not the answer I thought. Anyway, here's my little fire.
Just turn it on.
It's gas, you just turn it on. It would not work if you close up the top. So but I was looking for it, you have to open the flue. most people that have ever had a fireplace will turn it on and then smoke out their house. Dang. They either didn't make the fire enough to get convection going, or they forgot to open the flue. So the smoke, when it rises up on the warm air currents, goes outside the house. Look at this. This didn't go. It lit and then turned off, went out. So it's happy. But then I close the bottom off there, top's still open, and it goes out. Because the hot air rises. But the cold air can't get in with the fresh oxygen. So with my little setup here, I put a little divider in there. Now the hot air can go up one side, while the fresh oxygen and the cold can come in, and you get a convection flow, and this will stay lit. And while you're thinking of that, you had to have a lava lamp. Who has a lava lamp? Who has 2? 3? I forgot how many I have. But that's how they work. There's just a light bulb down here. So the blobs come down to the bottom, and they heat up by conduction. And then they expand. Decreases their density, so they float, and they come up to the top. But then as they cool, they contract, increase their density, and they sink back down. It's just convection going on in there. Through a lava lamp. Basic physics. Love that. This is still lit. If I pull it out, on. Now the hot air can go up, but as it's coming up, it's keeping fresh oxygen in the cold air from coming down, and it goes back out. So that's convection. Now I want to show 2 more fun ones with that. This is a heat lamp. Well, better show it first this way. It's just a bunch of wire on there like your blow dryer or space heater. When you send electricity through wire, it meets resistance. And so a lot of that electrical energy is converted to heat and transferred out. So I got a light source so you can see. Here's the wire. All right, now let's plug it in and begin it to heating up. Oh, look, you can see already, immediately. That's the convection. It's heating up the air next to it. That air expands and rises, and you're starting convection. You can also see that there's a little breeze in here, because as it goes up, it's getting blown this way, isn't it? But I think it's cool you can see it. That's optics, if you're curious. Hot air and cold air bend light at different amounts. So you can see edges between hot and cold air, or hot, warm, and even hotter air. That's why you see these little lines. So if I unplug it, it'll cool off, but not all at once, and that convection flow will start to decrease. Now, we're going to talk about radiation. That's the third method of heat transfer. This is radiating heat. Because the wire is hot, it gives off heat. And then that heats up the air, which then transfers heat through convection. But just because something has a temperature, period, if anything has a temperature, it gives off radiation. Thermal radiation. This you can see, it actually glowing. That when things get hotter and hotter and hotter, at some point they can actually give off radiation that's visible to our eyes, and we see it glowing. That's how lights work. Right now it still has a temperature, doesn't it? It's still giving off radiation, but we can't see it. This is the help see it. We can't see any visible light. It's giving off what we call infrared radiation. It's still a form of light. It just is not detectable by our eyes. You guys are giving off infrared light right now. We just can't see it. So when you guys come back from spring break, we have a thermal imaging camera that can just see infrared. And I'll aim at you guys, and it can detect the hot spots on your face and the cold spots. Because anything with a temperature gives off radiation. that is how these little toys, they're sold as toys now, work. And go figure, they're called radiometers. Anybody seen these before? They have little black and white vanes. A few of you. Well, the way they work with radiation, conduction, you need two materials in contact, or throughout the material, because they're touching. Convection, you need a fluid. You need to heat up something, and then it's transferred with that person. Radiation does not need a medium to transfer through. It gives it off in the form of electromagnetic radiation, light, whether we can see it or not. There's more forms of light we can't see than we can. And so that's how the sun heats us up. It gives off radiation, travels through empty space as a wave to us. It does not need a medium. This is partially evacuated, and if I take a light source, it's giving off visible light, but I can actually feel the heat also. You know, when you stand next to a fire, you feel warm? It's mostly because of radiation. If you're trapped in a room, it'll heat up the air, and convection will help heat up the rest of the room. It's not in, Canada. So the radiation goes and heats up the veins. And black is a better absorber of heat than white. I thought most of you knew that. You go out on a hot summer day and wear a black t-shirt, you tend to feel like you heat up faster. That's because black absorbs the heat better than white. So the black sides of these heat up more, and that makes a difference in the two sides, and it'll turn. Likewise, though, just like metal heats up faster than wood, it also cools down faster than wood. Same with black. It's a better absorber of heat, so it'll heat up faster, but it'll also cool down more quickly. We'll discuss that more after spring break also. Yeah.
You know what I'm talking about when I say radiant heating in houses?
Radiant heating, that is this radiation stuff.
How is any other sort of heating in houses or buildings different? Isn't it all radiant?
Is it all radiant? No. Think of your classic. You got a radiator. Probably guess why it was called that. You know, over here on your wall, those thin things that if you're in old buildings, it starts making noise and making clunking, and you think something goes. Well, what they generally do is it heats up. Through conduction, then, it heats up the air next to it. But then that air rises, and you get a convection flow. And it's through convection that most houses are heated up. Now we have gas heaters, right? They heat up the air. But then they force that air to convect and blow around your house. So it's essentially convection that heats you up. Radiant would be like geothermal or something, where just because it's hot, it gives off radiant energy. The radiator gives off heat too, so when you stand next to it, you feel warm. But its main purpose was for convection. Because only if you're close to it do you feel the heat. Especially if you're in another room, you don't feel the radiant. It can contribute. They usually paint radiators. That's here's another fun one. On this side, I have a bulb that looks like this. You can't all see it. I'm going to heat it up. Turn it on. There it is. On this side, I have a match. Some of you can see. And so, yep, it's on. I can feel the radiant heat. The dishes focus the heat. So, yeah, the light bulb on the left heats up, and it sends out radiant light. The dish focuses that light and sends it to the dish with the match, which focuses it onto the match head. So we're transferring radiant energy from the light bulb to the match head. And it doesn't need the air in between. Because the air near the light bulb heats up and goes up. And it creates a little convection in the room. But it would take a really long time to heat up all the air, which would heat up the match head. But here, see, do we see any smoke coming off of the match yet? This, you can just transfer through empty space, through radiation. It takes a few minutes. Sometimes you can see smoke Yep, I can see some smoke. I can see the smoke blowing off though. So there's a little currents in these rooms. So I'll keep battling while we're watching. But I've actually roasted a s'more this way. Marshmallow. I can put it at the focal point and just transfer this radiant energy. I cooked the hot dog too. It just took a while. But the hot dogs are already cooked, so they're safe to eat cold. I just want to warm it up and have fun. Anybody else see the smoke now? I can't. At least on this side. Let's see. So your superhero paper idea is due today. You guys have emailed it to me. There it goes. Well, the firecracker is a lot more fun. I take the firecracker to the match head because one, you can't all see it. Well, that's more fun. So radiant energy. I'll stop. I'll do this in a minute. But yeah, reminder, your superhero paper idea is due by the end of the day. And your homework on chapter 15 is due Sunday. We'll continue with this chapter 16 stuff when you come back and then finish it review and have an exam at the end of it. I hope you guys have a great spring break.